Hello friends, so today I am going to solve questions from heat and thermodynamics. So these questions are from the year 2024 and I am going to solve total 8 questions, and all these 8 questions are from the mains only. So the first question, it states that the PT diagram of an ideal gas having 3 different densities rho 1, rho 2, rho 3 in 3 different cases is shown in the figure. Which of the following is correct? So basic figure is given to us. We have PT diagram and we have rho 1, rho 2 and rho 3. Okay, and we have to find out how these rho 1, rho 2 are comparative to each other. Okay. So for that, because the density is given, so we are going to use the ideal gas equation, and from that we are going to come to the mass of the different bodies or gases whichever it is present there. So we start with our ideal gas law, and which gives us that PV is equal to nRT, where N is our number of moles, and this equation can be written in terms of our given mass and the molar mass times the constant as well as the temperature. And this can be further modified, and we can write this in terms of pressure only. So pressure will be equal to our can write this value over given mass oblique is volume, and this comes as RT divided by the molar mass, and this comes to our density RT oblique M. So if we look closely, we can say our pressure will be directly proportional to density given that this temperature is constant. Okay. So we can just draw the given graph and we fix the value of the temperature. So this is our temperature T, and we have pressure P, and we are given 3 different densities. So we have rho 1, rho 2 as well as rho 3. So we fix one particular value of the temperature. Let us suppose this is the value of temperature, and corresponding to this temperature we find out the value of the pressure. So for rho 1, the corresponding pressure is, let us suppose, P1. For rho 2, the corresponding pressure is P2, and for rho 3, the corresponding pressure is our P3. So from graph we can say, or from the equation, let me write it again. So we get the pressure is equal to density RT upon M. Now we have fixed one particular value of temperature, so we can say this temperature is constant. Therefore from here we can say our pressure P is proportional to our density. And from PV diagram, or rather we can say from PT diagram, we can write that from PT diagram we can easily see that our P1 is greater than P2 is greater than P3. Therefore, based on this, because there is pressure and density are directly proportional to each other, we can say our rho 1 is greater than rho 2 is greater than rho 3. So we can say that our rho 1 is greater than rho 2. So option 2 is correct. Option 2 is correct. Next question. It states that a sample of a gas at temperature T is adiabatically expanded to double its volume. The work done by the gas in the process is given. The adiabatic ratio is 3/2. So we are given adiabatic process. So we are going to start with our adiabatic equation with respect to pressure volume as well as the temperature volume. So we can say that for adiabatic process, we can write two relationship. One is our PV raised to power gamma is equal to constant, and second one we can write temperature volume raised to power gamma minus 1 will be also equal to constant. And we are given, or let's assume that our initial volume is V1. So you can say our initial volume is V1, which we assume is equal to V, and our final volume is our V2, and it is given that it is expanded to the double the initial volume. So this comes as our 2 times V, and gamma is given to us as 3/2, and number of this should be actually number of moles is our 1. And first of all, because we are supposed to find out work done, and work done in the adiabatic process is P2V2 minus P1V1, and that is divided by 1 minus gamma. That is a standard relationship. Okay. So we have to find out all these P1, P2 and everything. So we are going to start with our this TV gamma gamma minus 1 is equal to constant. So we can write this as our T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. Okay. And gamma is our 3/2. So we substitute it. So we get this as T1 V1, this will be 3/2 minus 1, giving us 1/2 is equal to, we have T2, and V2 is our twice of V, and here also we can substitute V1 equal to V, and this get twice of V raised to power 1/2. Therefore, and initial temperature, that is T1 is equal to T. So we substitute T is equal to, this comes as V upon twice V whole raised to power 1/2 is equal to T2, and this V and V cancel out. So from here we get our T2 is equal to T divided by square root of 2. Okay, so we were able to find out our this temperature relationship, or we can say final temperature. Now we come to the original equation of our work done, which gives us that our work done in adiabatic process is, let us suppose, given as W. So we can write this, our W will be equal to P2 V2 minus P1 V1 divided by 1 minus gamma. And we can also use our ideal gas equation, that is our PV is equal to nRT and number of moles are 1. So we particularly can write this as P1 V1 is equal to our RT. And okay, along with this we can also write that our P2 V2 is equal to R times T2. Okay. And we know the relationship between T2 and T, so this comes as our R times T upon square root of T. So we got our P1 V1 and we also got our P2 V2. So we substitute and we get this as the work done is equal to 1 minus gamma, that is 1 minus 3 by 2, and P2 V2 is our RT square root of 2 minus RT, which is our P1 V1. Now it is quite easy. We get this as, this will be our RT, we can take common, and in the numerator it will be coming as minus 1 by 2, and from here we get this as 1 upon square root of 2 minus 1. And now we can just sort it out and we get this as our RT, or we can say, we can write this as twice RT. This will be minus 1 upon square root of 2. And we can take square root of 2 as LCM. So this comes as twice RT divided by square root of 2, and this comes as square root of 2 minus 1. Now we can rationalize it. And this gives us that our work done will be equal to, it comes as twice square root of 2 divided by 2, and this is RT square root of 2 minus 1. So here 2 and 2 cancel out and we multiply inside with square root of 2. So we get this as our RT, giving us 2 minus square root of 2. So this is our final work done, RT 2 minus square root of 2, which is option 4 is correct. Option 4 is correct. Next question. It states that the heat absorbed by system in going through a given cyclic process is, so basic PV diagram is given to us. We have cyclic process and lying between, we can say, of the volume of 60 and 340, and the pressure is 60 also at 340 also. Okay, so if you remember, this is cyclic process, and for cyclic process we know that the change in internal energy is equal to 0. So we are going to use first law of thermodynamics. So you can say first law of thermodynamics, and which gives us delta Q is equal to over delta U plus W. And we have a cyclic process. So we know that for our cyclic process, delta U is equal to 0. Therefore, we can say that our heat will be simply equal to our work done. And work done, we know, is our area of our this PV diagram, which is equal to area of PV curve. And so we simply substitute, because this is a circle, so we can write this will be equal to over pi multiply by, we have this as okay. So this is our sphere, circle rather, and we can write it as the difference is 340 and 160. So that will be coming as our, 1 second, if I'm not wrong, this is 60 and 340. So this entire will be coming as 280, and half of that will be 140. Okay, and okay, yeah, that will be 140. So we can write this will be equal to 140 and kilopascal 10 is power 3, and this will be equal to 140, and it is given in CEC, so we can say this will be equal to 10 to the power minus 6 meter cube. So we get that our delta Q will be equal to 61.6 joules. Okay. So we at option 1 is correct. One is correct. Next question. It states that a total of 48 joule heat is given to 1 mole of helium kept in a cylinder. The temperature of helium increased by 2 degrees centigrade. The work done by the gas is R is given as 8.3. So we have a helium 1 mole, and we know that helium is our monatomic. So we are given as helium, which is monatomic. Therefore, we can say that our C of V will be equal to 3 by 2 times R, and our C of P will be equal to 5 by 2 times R, and we are supposed to find out work done, and for that we are going to use first law of thermodynamics. Okay. And you can say first law of thermodynamics, which gives us that our heat will be equal to change in internal energy plus work done, and heat is given to us, and the temperature it says is increased by 2 degrees centigrade. So we are going to find out our delta U, change in internal energy, which will be equal to our N C of V multiplied by delta T. Number of moles is our 1, C of V is our 3 by 2 times R is our 8.3, and the change in temperature is our 2. Therefore, we get this our delta U is equal to 24.9 joules. Now it is quite easy, so we can simply write that our work done is equal to Q minus delta U. Heat given is given to us, that is 48 minus 24.9, so we get our work done, that is W is equal to 23.1 joules. So we have option 4 is correct. Is correct. Next question. It states that two different adiabatic paths for the same gas intersect two isothermal curves as shown in a PV diagram. The relation between the ratio of VA upon VD and ratio of VB upon VC is. So we are given two isothermal curves, whichever AB and BC, and adiabatic are our AD and BC. So they are intersecting at various values of temperature, various values of pressure as well as various values of volume. Okay. So basically this is cyclic process. So it starts from A. We can assume it starts from A, goes to B, then to C, then to D, and come back to our A. So path AB is our isothermal. We have path AB, which is isothermal, and temperature that is given is our T1. Therefore, we can say that the temperature at A will be equal to temperature at B will be equal to T1. And we can use our, we can use our ideal gas law. We can say that our ideal gas law, which gives us that PV is equal to nRT, and here on the right side N, R and T all are constant specifically for this path AB because it is isothermal. Therefore, we can write it as our PA VA will be equal to PV and VB. And we can make adjustment in that, and we can write this as VA upon VB will be equal to over PB upon PA. So this is one part of the ratio. Now we come to the other part, that is a path CD. And which is also isothermal but at a different temperature T2. So this is our isothermal and it is at temperature T2. Therefore we can write that TC, temperature at C, is equal to temperature at D is equal to T2. And here also once again ideal gas law, for both the points we can write this as P of C multiplied by V of C will be equal to pressure at D multiplied by volume at D. And we can find out the ratio. So we can say ratio of our V of C upon V of T is equal to P of D and P of C. And we have to find out VA upon VD. Okay, later on we can just manipulate that, it's not a big issue. So this was with respect to our isothermal. Now we come to our adiabatic process. So we know that our B to C and D to A are adiabatic. So they are adiabatic process. Therefore we can use that our T multiplied by V gamma minus 1 is equal to constant. And so we have two paths. Let's first of all consider for BC. So we can say for BC, and we can write this as temperature at B, volume at B, gamma minus 1 is equal to temperature at C, volume at C, gamma minus 1. And we know that the temperature at B is our T1 and temperature at C is our T2. Temperature at B is our T1 and temperature at C is our T2. Therefore we can write this equation as our T1 VB gamma minus 1 is equal to T2 VC gamma minus 1. So the ratio of the volumes VB upon VC gamma minus 1 will be equal to T2 upon T1. And you can further you can say for reformulate it, you can write VB upon VC is equal to T2 upon T1, and this comes as 1 upon gamma minus 1. Similarly, we write for our path DA. Path D to A, we can write this as our temperature at D, volume at D, gamma minus 1 is equal to temperature at A, volume at A, and we have this as gamma minus 1. And we know that the temperature at D is our T2 and temperature at A is our T1. Therefore we get this our T2 VD gamma minus 1 is equal to T2 and TA is 1. So So this comes as 1 VA gamma minus 1. Same way, let me write it directly. We can say that our VA upon VD is equal to T2 upon T1 and 1 upon gamma minus 1. So we get two equations from adiabatic, that is our VB upon VC is equal to T2 upon T1 1 upon gamma minus 1, and second we get that VA upon VD is equal to T2 upon T1 1 upon gamma minus 1. Thus from here we can write that our VA upon VD is equal to VB upon VC. That is our final result. So we get this as VA upon VD is equal to option 3 is correct. Is correct. Next question. It states that a diatomic gas gamma 1.4 does 100 joule of work in isobaric expansion. The heat given to gas is, so this is isobaric, so pressure will be our constant. And for that we know that work done is equal to P delta V. Okay. So we can say that for isobaric process we have work done is equal to P delta V, and in terms of ideal gas law we can write this as NR delta T, and so it is given as 100 joule, so we substitute this as 100, and so we get this as our 100 is equal to our R times delta T, and from here we can write that our delta T is equal to 100 upon R. So we have to find out the heat given, and this is a constant pressure. So for diatomic gamma is given to us, so from here we can find out C of P. So you can say our C of P will be equal to gamma R and gamma minus 1. So it comes as 1.4 times R and 1.4 minus 1, which gives us 3.5 times R. Now we can easily find out the heat, that is Q. So we can say heat Q will be equal to N C of P multiplied by delta T, and C of P is our 3.5 times R and delta T is our 100 upon R. So here R and R goes away, and this gives us that Q will be equal to 350 joules. So option 1 is correct. One is correct. Next question. It states that the volume of ideal gas gamma 1.5 is changed adiabatically from 5 liters to 4 liters. The ratio of the initial pressure to the final pressure is. So this is adiabatic process. So we can use the standard equation for our pressure volume relationship. So we have our adiabatic process, and which gives us that PV raised to power gamma is equal to constant, and which can be further written as P1 V1 raised to power gamma is equal to P2 V2 raised to power gamma, and volume is changed given as 5 to 4. So we can say that our V1 is equal to 5 liters and our V2 is equal to 4 liters, and gamma is given to us as 1.5. Therefore, we can say that our P1 upon P2 is equal to V2 upon V1 whole raised to power gamma. So this comes as 4 upon 5 and raised to power, this will be our 3 by 2. So we get this as 3 by 2, and this we can write as gamma square root, and okay, so this can be written as 4 by 5 multiplied by 4 by 5 1 by 2, and so now it is quite easy. So we get this as our 4 upon 5 as it is, square root of 4 will be 2, and this will be square root of 5. So we get this as 8 5 square root of 5. So option 3 is correct. Next question. A real gas within a closed chamber at 27 degrees centigrade undergoes a cyclic process as shown in the figure. The gas obeys PV raised to power 3 RT equation for the path A to B. The net work done in the complete cycle assuming R is equal to 8 is given as. So we have a PV diagram, and this is basically cyclic process A, B, C and back to A, and we have to find out the net work done. So for individual path we can just find out their individual work done, like work done for AB, work done for BC and work done for our CA, and add them, we are going to get the answer. And let us start for our AB. So we can say work done for AB that is our WAB will be integration PdV, and the relationship is given between our P, V and RT. So we substitute it value of P, we get this as our RT upon V cube dV and integration. And if we see the volume changes between our 2 and 4, so this comes as 2 to 4. RT we can take as common, so this comes as our RT, and we have this as 2 to 4 and V raised to power minus 3 derivative of V. Now it is simple integration, and R is said to be taken as our 8 and temperature 27 degrees centigrade, so that will be 300 Kelvin multiply by this will be minus 1 by 2, we can take as common, and we are going to get this 1 upon 4 square minus 1 upon 2 square. So we get that our WAB will be equal to 225 joules. Now we come to the path BC, which is basically our pressure is constant, that is our isobaric. So we can say path BC, we can say WBC is equal to pressure is constant, and we have integration from 4 to 2 derivative of V. So this gives us pressure is over 10, and it will be coming as 2 minus 4, which will be giving us minus 20 joules. And we come to the path CA, which is our volume is constant, so its work done will be equal to 0. So we can say path CA. So work done with CA, because there is no change in volume, volume is constant, so WCA is equal to 0. Therefore we can write that total work done W is equal to WAB plus WBC plus WCA, and we substitute the values. We get W is equal to WAB is 225 minus 20 plus 0, giving us that W is equal to 205 joules. So we have option 2 is correct. Is correct. So these were the 8 questions from the year 2024, and this was the part second. I forgot to mention, this was our part 2. So 2024, this was part 2. So remaining question for the year 2024, mains as well as advanced, we will try to cover in the next. So might be part 3, or if required we will do part 4 also. So this completes all the questions. Thank you.